But most of his time doing is working on Haskell.
Yes. Don't tell our boss.
Programming
No.
and trying to understand industrial impacts of functional programming, non-programming techniques. So we're going to have the treat of, I think this is the first chalk talk I've seen at JHU in our CS seminar, but I'll hand it over to Edward.
Yes. I used to teach math, so. That, and I don't really have a set of slides for this that I really like. So what I want to talk about today is perhaps a slightly different way of building a database. This actually kind of, and some of these pieces will be for more traditional database use, and some of them will be for OLAP style queries rather than OLTP. And really, sort of this kind of got started because I was looking around. I started working on a dialect of data log for something, and the tools I wanted to use were patented. So who says that patents don't spur innovation? They kind of drove me off into theoretical la-la land, and then I had to kind of piece together enough stuff to come back and try and see if I could actually build something that was worth having. Okay. And most of these tools are actually fairly new in the world of computer science. Cache oblivious algorithms are, like, they go back to, what, Prokop's thesis from 1990, somewhere there. I guess that's not that new. The succinct data structures go back, those are actually new, like the last several years. And so those are the two tools that I want to talk about today. I'm going to talk a lot less about the cache oblivious side and a lot more about the succinct data structure toolbox. Even though the cache oblivious structures may be more relevant to actual proper building a database. I think the succinct ones are more interesting, and I have more to say there that hasn't been said before, at least by me. And so I guess what I want to start with is the notion of we're going to build a database a very weird way by basically just starting with the notion of storing a bunch of bits. How many people here are familiar with, like, bit indexes? Is that term crossed? Okay, maybe a half dozen, a dozen. Okay. So let's just talk about how I can store a vector of bits. Actually, I'm going to take this off if I'm going to be using chalk. All right, hopefully that didn't destroy the mics. All right. So if I have a vector of bits, and I don't know anything else about it other than how many zeros and ones I have in it. So I have n bits, of which k of them are ones. Then what I could do is if I stored k, I could compress this bit vector by just saying, well, there are n choose k possibilities. And so I could represent this by saying, well, which one is it? And just write it down as a number. And that number would take, log n bits, potentially plus 1 because you have to round it up, to the number of bits. Okay? So this is the amount of information. This is the zeroth order entropy of this bit vector. How are people on entropy and information theory? I can... Some nod, some... okay. So this notion that I can store this sometimes in much less space and sometimes in a little bit more, because we obviously can't always win on compression. This works out very well for when there are very few cases. For instance, if I had one bit inside of here, then this is going to be basically log of n. It's just which one is it? And then if there were two, then it's going to be something around n squared. What are or not n squared? Something around 2n, right? It's going to be which one's the first one, which one's the second one, and then kind of quotient out the relative order of the two, and so on and so forth. And as we get up around k being n over 2, this gets large again. This becomes roughly the size of the bit vector plus a little bit, because we have to. We can't always win. But in general, if this is heavily lopsided, then we win. Okay. So we could store this. It's a terrible representation. And I just stored a number. So what do I have to do in order to do any sort of indexing on this? I probably have to decompress it or something. So what isn't obvious is that there are algorithms that can store this in not much bigger than this space and still support forms of indexing. So I want to be able to index directly on my compressed representation of my data. Okay, and that's really what the notion of a succinct data structure is all about. Okay, and so that will at least kind of set the stage. So we're going to try and store our data in a optimally or near optimally compressed form, and then be able to work directly on it in its compressed form and perform the indexing operations without decompressing. Okay. So a succinct data structure is one that is that can be stored within an additive little o term of entropy, of zeroth order entropy. So we're going to say that we're willing to, if H0 is n, if we're willing to add a little o of n term. So this will vanish as n gets large. Okay? So succinct, I should write bigger. Succinct is n plus little o of n. And there's the notion of like implicit, which is n plus 1, which is where we started, and compact, which is big O of n, where these are in terms of n being zeroth order entropy. Okay. So this is my goal here is to be able to store data in about this much space. So if little o of n here is actually like n divided by log of n, and I have something about a gig of data, I have a 30th of a gig worth of indexing. And if I start growing to a terabyte, I might have a 40th of a terabyte worth of indexing. And so it's getting comparatively smaller as my data set gets larger. It's not growing like n log n, and starting to consume more and more time. As my data sets start to grow to the petascale and beyond, I really start to care about those factors, and I really start to get some decent wins here. Okay, so that's getting a little bit ahead of myself. Let's focus just on the bit vector and see what kind of indexing we could do on this. And I'm not going to focus too much on how we can implement succinct data structures. I want to focus a lot more on what we can do with them. You can dig up the papers on how it's built. But what we can do with them is something that hasn't been explored very thoroughly. Okay? So, let's use this. Actually, let's go back here. So what I want to do here is at least convince you that there are a couple of interesting operations that we can perform on a bit vector without taking too long. So let's at least get the time right. Let's actually say that there's a couple of O1 operations we can perform on a bit vector. We're not even going to compress it yet. We'll just do it on the raw bit vector. Okay? And the two operations that I want to be able to perform, one is called rank. So rank alpha Si is going to tell you how many alphas there are in S up to position I, inclusive, actually. Okay? So if I ask this thing for rank, I'm going to start indexing at 1 just to make things look pretty. So if I ask for how many ones are there up to position 5, it's going to tell me 3. Or if I ask for rank of zeros up to position 3, it's going to tell me 1. Okay? So this is just a prefix sum, because you can always derive rank of 1s from rank of 0 here by subtracting it from I. Okay? So we can just calculate rank of 0 or rank of 1 here. We don't need to store both. And how could we calculate rank of 1s? If I was willing to double the original bit vector size and not try and get it down to the super compressed optimal form, what I could do is I could take my bit vector and store a second bit vector. Okay? And I could break this bit vector up into chunks we're trying to shave a log factor or something to get down to n over log n, so that we're little o of n. So if we broke these things up into chunks that are of size log n, then I can know that if I were to store a prefix sum up to the beginning of the chunk, then, well, that can be at most n, so it'll fit in log n bits. So I'll never more than double my storage space to do this. So I can just store how many numbers are there up to the beginning of the chunk. I'll actually do it for the beginning of the chunk rather than to the chunk, because it simplifies corner cases. So here there are 3 ones before we get to this chunk. Here there's a total of 6 ones. Here there's a total of 10 ones. Right? And so if I wanted to actually give you, what is the rank? How many ones are there up to, say, this position here? What I could do is I could divide by log of n. That'll give me a quotient and a remainder. The quotient is going to tell me that I should look in this bucket and take this number. The remainder is going to tell me how far in I should go. I will mask this off in pop count, and we can do pop count in O1 in a word machine. So pop count is just count how many ones there are in the masked off word. Okay? And so at that point in time, we have computed rank in O1. So I just wanted to demonstrate that it is possible to compute rank in O1. Okay? And this is key to everything that I want to talk about today. The fact that we can do it in less space, the fact that it is succinct, is interesting from a theoretical standpoint, but may not win on constant factors. And as a matter of fact, many of the cases that I'm going to be working with today are actually the worst case for this, for H0, because I'm going to be working with things where it's n over 2, which is the high point. So I want n choose n over 2. It's not going to be that great to use a compressed representation. So if I happen to choose a bit vector representation that is suboptimal, that just does this, then I really am not hurting myself too hard. Okay, but I can always go back to using Raman and Rayo or one of these other formulations that gives me the space.
Okay, maybe this is a dumb question, but what if log n is bigger than a word? The pop count or whatever.
Well, I'm assuming that we're working on machines that exist. So it's a dirty hack. You can steal the log from just from that. If you want to start trying to do it on non-word machine models, then you actually there's other lookup table tricks you have to play. And this is not the optimal representation. You can actually do this where you don't do log size chunks, you do it in log squared size chunks. And then you have to do things within the chunk sizes, and you can do all of that by lookup table. This is an implementation that works in practice on real hardware at real scale. So this will handle any amount of data that you could conceivably index on this planet. And to do the proper, I have many galactic clusters worth of computing power at my disposal version. You have to actually use lookup tables. Those ones are tackled by the paper. I'm going to skip that today. So we've talked about rank, which is just, again, sort of a prefix sum. Tell me how many things there are up to a given position. I'll describe the other operation, but not give you the O1 implementation. It's just not informative. And that is called select. And select will tell you the position of the ith alpha in S. So if I ask to select the position of the third 1, it will tell me 5. If I ask to select the position of the second 0, it'll tell me 4. Okay? Now, mathematically, there's an interesting connection between these two properties. And that is that they form a Galois connection. Okay, and I'm going to probably in one direction there's a Galois connection, in the other direction there's a one-sided inverse. So there's a lot of ability to get rank from select and select from rank and transfer information between these two things. So if I look at If I select the position of the third one, and I ask, how many ones overlap to that position, it better tell me 3. On the other hand, if I ask how many zeros there are up to a given position, and it tells me 2, and I select the position of the second 0, it better be less than the number I fed it in the first place. So in one sense, it's an actual equality. In the other sense, it's an inequality. So in one order, it works one way. In the other, it's a stronger condition. Okay? So what we have is that rank alpha S. I'm going to drop the S's. They'll be implied throughout the rest of this talk. Rank alpha of select alpha of position I had better be I. And select alpha of rank alpha I is going to be less than or equal to I. So this is that rank is a left inverse of select, and this is that select and rank form a Galois connection. Okay? This Galois connection gives you some nice properties. We can use this to say that if you don't know how to implement select, you can always binary search for it. We have a well-founded domain. We have a Galois connection. We can search through it. We can find the place where it trips high. Log time. So we can always implement select in a rather poor manner by just binary searching. In practice, we'll probably set up a little lookup table that says this is like some quick start information and then just do linear scans, because on real hardware at real scales that works. And there are papers showing the right way to do it from a theoretical standpoint and the right way to do it from a practical engineering standpoint. I don't need to belabor the implementation details. Okay, so rank and select are the primitives that I want to talk about today. We're going to build everything, with one or two exceptions, out of these things. Okay, so it's not immediately obvious that it's enough to build an OLAP-style data warehouse, but we'll see. All right, so absolutely.
Yeah, so I'm a little confused about what we're trying to index, because this is a practical talk.
Yes, right now all we have are bits.
Right, so why are we indexing bits?
Because I need a building block to build the next building block.
So bit indexes tend to work best in the context of having low cardinality data sets of types. And so when you've got a low cardinality set,
yes, and I'm going to try and break that rule. So why don't we see where this is going real quick? And I think I'll answer your question almost implicitly through the next 10 minutes.
Great.
And if not, feel free to interject again, then I'll go down that rabbit hole. All right. So what I want to do now is I want to deal with alphabets that are not ones and zeros. Because I need to be able to deal with arbitrary strings or whatever the heck I want to store in my database. And so what I'm going to do right now is I'm going to assume that you have some order-preserving prefix-free code. Not a Huffman code, a Hugh Tucker code, an arithmetic code, something that you want to use for the data you want to store. Now this is actually a pretty big assumption, because I'm assuming that you have a model, basically, by saying this. I'm asking you to give me a model for your data. And in exchange, I'm going to try and index it relatively efficiently. Okay, so let's just talk about how we can walk any sort of prefix-free code and build rank and select on symbols out of that code. So if I have a string, how many people here are familiar with Huffman coding? All right. So I assumed that one was going to be a near unanimous yes. I'm glad. So let's say that you have the string like FF, CD, C, F, A, B, CD, F. Okay? And you had a Huffman tree. I don't know. We'll put the A and the B over here. We'll put an F over here. And we'll shove C and D over here. Okay? So we have this string, and we want to Huffman code. Or we want to encode it as a bit stream using this tree. right? 0 on the left, 1 on the right. So what is this? This is 1, 1, 1, 1, 1, 0, 0, 1, 0, 1, 1, 0, 0, 1, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, 1, 1, 1. But if I jump in the middle of that bit string, it doesn't mean anything to me. I couldn't put a rank and select structure on that and tell you anything about the data set. Each one of these bits could be any one of these 4 decisions that are implied in my tree. They could mean different things. Okay? So I stored my data, but I'm not indexing into it effectively. So I've got 4 decisions that I want to make. I want to store the same number of bits in a different way. And this gives rise to something called a wavelet tree. Now, there's no wavelets in a wavelet tree. It's kind of oddly named. It's named by analogy, so we'll try and get there. But so if you know what a wavelet is, it gives you no insight into this talk. I didn't name it. It's not my fault. So what we're going to do is we're just going to store which of these bits were decisions being made at the top of the tree. Well, this one. I mean, I shouldn't circle them. This one, 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 and this one. So let's just grab those bits. Let's stratify our bits into distinct decisions so that we can say what they mean. Okay? So this is 1, 1, 1, 1, 1, because CDC is on the right-hand side. F, 0, 0, 1, 1, 1. Okay? And now, over here, we just want to store the bits that represent this decision, which are this one and this one. So we want a 0 and a 1, because those are out of the ones that were A or B. Which were they? Were they A's or B's? So this is not a bit index in the classical sense. It's a dependent bit index. We've made the decision at the top level and then classified everything either into bin 1 or bin 2, and now below that we're only storing the things that go into bin 1 or bin 2. Okay, so normally if you had a classical bit index, or you had a pair of bit indexes, like one for the first bit of your code and the second one for the second bit of your code, it'd be terrible. You really need to kind of walk both of them in parallel, do ands and ors, and and it was great for Sybase. And it did a lot of good for its time. I don't mean to denigrate a whole era. But I want to try to build something. We want to build something a little bit different here. And so what we're going to do now is we're going to say out of the ones that went right, what decisions did they make? And so an F is on the right, an F, a C and a D and a C. So those are all on the left. F, C, D, F. Okay? And then down here we'll put one last kind of level to the cascade, which is, out of the things that were C's and D's, which way did they go? So, C, D, C, C, D. I think I got everything correct there. Does that look right to folks? I apologize for my small handwriting in a large auditorium. All right? So, now that we have this, let's look at how we can implement rank and select on this alphabet, because now it starts to get interesting. I want to be able to answer questions about how many C's are there in this string up to a given position? How many F's are there? How many things less than or equal to C are up to a given position? What's the position of the case C in this string? So I've got data in some arbitrary order here, and I've put it in order by my code. We can start talking about these things as a form of stable sort in a second. But let's actually see that we can implement rank and select first. Okay? So if I wanted to know the rank of how many, I don't know, let's use C, are there in this string up to the 7th position. What I can do is I can use the fact that I encoded C as 1, 0, 0 in my tree. That's its path. It goes right, then left, left. And I can say, well, what are the rank of 1s, because it's the first digit, in this thing, up to the 7th position? And now they tell me, well, there's 6 1s. Right? Because 1, 2, 3, 4, 5, 6, 7. The A is included, and that was a 0. So 6 of those first 7 digits were 1s. Okay, fine. Come down here and tell me what's the position. Not position. How many zeros are there up to the 6th position in this array? So we've got 3. And so we keep chaining the answers as we go down the tree. So we're going to take the rank from the previous answer and use it as a dependent rank on the next answer to get the next answer. And now we're going to come over here and we're going to say, how many zeros are there up to the 3rd position? And it says 2. And we go, great, there are 2 C's in this string up to the 7th position. Okay? Each one of those queries took us 01. So it takes us the code length of time in order to answer this query. This works independent of the data set size. It depends on the code length. Does that start to indicate where this is going for you? Okay. And so we can now do rank in time length proportional to the code length. And we can do select similarly. So select, we can also do an 01. I didn't show it. But we do select by walking up the tree. Okay, so we start at the bottom and we say, well, what was the position of the... We said that there were 2 C's. What was the position of the second one? We start down here at the bottom. We walk the code backwards. We say, okay, great. Select the position of... We wanted the second one. The second 0. It tells me 3. Select the position of the third 0. It tells me 5. Select the position of the 5th 1. It tells me 5. And it tells me that the second C is right here. Okay? So what we've done is, if we look at this data structure in one way, it's just a way to amp up. It's a way to lift rank and select to any compression scheme. Any prefix-free code works. Okay? And we'll need later the fact that I tend to want to use this on order-preserving compression schemes, where if 2 things were in order before, they wind up in order afterwards. Okay, so I care about compression schemes where this alphabet actually stays in order and I don't do arbitrary Huffman coding. In practice, preserving order costs us nothing with an arithmetic code. It's kind of what you do. And for Huffman codes, going from Huffman to Hugh Tucker costs you 2 bits. So it doesn't cost you in practice a whole lot of data. It's still data, but order preserving isn't a big deal. And we're going to be talking a bit about what this means from an entropy perspective later, because this doesn't actually take space based on the code length. It does in a little o term, but not in the primary term. Because remember, each one of these bit vectors is stored based on its 0th order entropy. So when you work it out, the space of this is actually largely independent of the code. The little o term changes, but the big O term, in the limit, the space of this is dominated by the complexity of these bit vectors. All right. So you've at least got the notion that rank and select can be applied to arbitrary alphabets, not just bit vectors. So if you envision one of these things as a column in a data store, where the wavelet tree that we're storing is taking my data from whatever the order that my rows happen to be stored in my data store in to what the feature it is that I'm trying to extract from my data set wants to be in. I can then answer questions about how many things have a given feature up to a given row number in my database, and I can answer questions about ranges of rows in my database if I know the row number from here to there. And if I have multiples of these structures that agree on the source order, I can walk up the tree to tell me what's the position. I should care about walking down the other tree to find out the attributes of that thing. So if I want to walk between, I can move up one wavelet tree and then come down another to answer questions about other attributes that are related to attributes I care about. Okay? So this is where we're going to start trying to turn this into something that more resembles a database. Or at least an OLAP-style data store. Okay, so now, the next piece I'm going to need, how many people here are familiar with Morton order? All right, so about a dozen people. So, we're going to take a brief detour through optimal matrix multiplication, or at least the idea of like how you can store data in a way that you don't necessarily need to know about the cache sizes that you're working with. So if you were to store a matrix for multiplication, you might store it row by row, or column by column. But if I needed this data all of a sudden by its transpose, if I needed it in the opposite order, if I chose wrong, then I have to pay to transpose this. Okay? And so I'm running through and I'm grabbing an element from here, an element from here, an element from here, and I'm going through. This actually is like the absolute worst case from a cache perspective, because I'm grabbing things that are as far apart as they possibly can in stride to convert from one order to another. Okay? And so there are solutions. You could pick a block size, and then you can break it down into the blocks. But now you have to know appropriate block size for your platform. And so that becomes a tuning parameter that you now have to optimize on every architecture you pick, and you're going to be optimal for one of your caches or something. Another option is to pick all of the block sizes. And what I mean by that is to say, what we're going to do is we're going to effectively interleave the bits of my two keys. Now this has some real problems that we're going to talk about, but it's a starting point. And then we're going to try and talk about how we can try and fix those problems. So what I'm going to do is if we just say, so this comes before this, the lines that I'm drawing are just kind of indicating the relative order of my data. You can do kind of an arrow that way. So if I have 2 bits worth of, 1 bit of data here, and 1 bit worth of data here, what I want to store this one, then this one, then this one, and then this one. Then this is 0, 0, 0, 1, 1, 0, 1, 1. Right? So the first bit is the y coordinate. The second bit is the x coordinate. Or, with a leading bit here. So I guess the 2 bits. Okay? And then if we wanted to store 4 bits of data, 2 bits from one column and 2 bits from another, we would have sort of a z made out of z's. And if you work that out, that should follow the basic binary arithmetic progression. Now, Morton order is a terrible space-filling curve. It has all sorts of bad properties relative to the Hilbert curve, etc. It has some nice properties in terms of how we can calculate with it, though. And so I'm going to stick to this curve despite the fact that other ones actually have nicer theoretical properties because they have worse theoretical properties for what I care about today. Okay? Some of what I'm doing here transfers to working with Hilbert curves. Okay. Now, traditionally, Morton order is applied to keys that have the same length. Basically, you have 2 integer keys or something like that. There's a problem with this, though. This gives a good traversal order if both of those keys use their full dynamic range. If one of them, say you had 2 32-bit integer keys, though, and one of them was only using like its least significant 8 bits, and the other one was using its entire dynamic range, then what you get is that you're basically you're giving each one of them a choice. You're giving each one of them a chance to give you a bit. And so you're kind of borrowing some of the order information from one and some of the order information from the other. But if you're not using the full dynamic range of your key, then what's going to happen is you're going to say, here's something interesting. And the other guy says, I pass. He gives you a 0. The other guy says, here's something interesting. The other guy passes. He passes 24 times in a 32-bit key, trying to get down to the least significant 8 bits. And then he finally says, okay, here's some information. Okay? He's not participating in the indexing process until 24 bits later. So you have 1 2 to the 24th of an index on this key. You have basically 1/16 millionth of an index. It's not a great index. You're not really getting a whole lot of information about that key. Okay? And so this actually brings us a little bit back to our Huffman coding here. So you can give me instead a code, an order-preserving code, preferably, for your data set. Then what I can do is I can interleave the bits from your compressed data streams for each column. So what you've given me is a model. You're trying to represent your data set in the least amount of bits. You're trying to say your column in the least amount of bits in a completely independent manner, not caring about co-coding between different data sets, etc. What you're doing is you're giving me a compression scheme, and I'm not going to use your compression scheme for compression. We just indicated that this thing doesn't really care. It takes the same amount of space, roughly, regardless of what order-preserving compression scheme you give me. I'm not going to use your compression scheme for compression. I'm going to use it for indexing. I'm using your compression scheme as a model of your column. And now I want to use that to provide me with a fairer indexing scheme. So what we're going to do is we're going to interleave the bits of your two compressed bit streams. And when one of them runs out of bits, we just keep taking from the other. Like if we have more than two columns, obviously, we're just going to keep taking round robin across the columns in the same order over and over again until one of them stops giving the interesting bits. And we're just going to keep skipping it. We're going to keep going until we go. So this isn't really space filling. It's more density filling at that. You lose dimensions as you go down the tree. So it kind of loses some of the properties that we expect from Morton order. You can view it as Morton order by saying, well, we'll take the length of the longest code and we'll zero pad all the other ones. Then it retains all the same properties that you're used to out of Morton order as a space filling curve. I don't know if that's particularly useful. We don't actually store the zeros in practice, etc. But it at least lets you keep the same mental framework. Why order preserving? The reason why we want to preserve order is that what happens then is that all we do is we distort the z's that you had in the original Morton order by kind of shoving more stuff nearby what you already have. And I'm trying to give intuition for this rather than full rigor, but we can talk about that in a little more detail. So the idea is that what we're going to do is we're going to try and warp these z's so they fit the data that you have. The shape of the model, at least, that you have. Not the data. They're data oblivious. The shape of the z doesn't change based on the data. It changes based on the model. So if you have a good fit to your model, we're going to perform very well. If you have a poor fit to your model, we're going to run into some corner cases that may suck. But at least intuitively, if you give me a good model, I will try to index into it efficiently by interleaving the bits of your keys. And so what this gives me is a composite index. It's one index to govern my whole data set. Okay? And it's not a great index. It's not a bad index for anything, though. And that's the interesting properties that it has. Okay, so I'm going to try and at least sketch how we can view the properties of this index, what it kind of means from an information theory perspective, and then how we can actually use it to do some queries over a data set that we might care about. I think that will make effective use of the time here. How am I doing on time, by the way?
About 20.
Okay, about 25 minutes. Okay. This thing went dead. So much for Google's battery life. Let's try and steal this whiteboard here. So what I want to do now is show what a data set that actually is stored this way would kind of look like, perhaps. So if we have, I'm going to pick a terrible example. Let's say you have customer sales data. And again, I haven't given you any sort of mutation primitives yet. We'll retrofit those on after the fact. Okay? I'll show you how we can do mutation after we get a query out of this thing, and so that it's worth building, at least. So what I want to do is I want to store my data in some kind of composite order where I'm interleaving my order for my different compression schemes. And then I also only have to logically interleave them. I don't actually have to physically interleave the bits. You actually have to pay for shuffles. I blogged about that at some point, and I can provide a link after the talk. So what I want to do is, let's say that we have a customer database, and we've just done some sales, and we've got your standard kind of OLAP data store, where we've got customer, the year, month, and date that they made the purchase, and what they bought. And we want to do something like, just tell me all the sales that there were in 2012. And I want to do this without paying per row. I do not want to pay any cost that is proportional to the size of the data set in any way, shape, or form. Here. Okay, I want to be completely data set agnostic. If you have yottabytes of data, I want to take the same time. Okay? When we add mutation, we're going to have to give up that property. But for right now, I just want to have it completely data set size agnostic. Okay? Well, it's not immediately obvious to me that you can do almost anything on a database that is data set size agnostic. At least it wasn't when I first started working on this. So what we're going to do is we're going to basically take our composite index, the sort of order that we're looking at here, the FFCDC, this code in the middle, the order that the rows are coming to us in, will be given to us by this composite interleaving of our bits from our different data sources. The order that we're putting them in will be the individual columns. So we're going to have one wavelet tree per column here. So we have customer, year, month, date, product, and each one of these is represented as a wavelet tree that goes from our composite order to the individual order of the column that we're interested in. Okay, so I'm storing my data set in this sort of organized into runs of things that are kind of showing the top bits of each one of my keys. Okay? So now let's say that I wanted to do total sales for 2012. Okay? This is a terrible example because it doesn't kind of hit the scale that we care about, but it's something that doesn't hit anyone's proprietary information. And so what I want to do is talk about how bad it is to answer a query about 2012. Just talk about it in the abstract without even really caring about what the query is just yet. Okay? And to do that, I need to first kind of reason about a couple of properties that all data that happens to be stored in lexicographical order has. Okay? If you have data that's stored in lexicographical order, and it's a series of bits, the most significant bit that is in that data set goes from low to high at most once. Right? It's in lexicographical order. If this property was violated, then something over here should be over here instead. You know, we can't have multiple pulses in this wave. Okay? Now the next most significant bit can at most double in frequency. It can go from low to high here, gets a chance to reset there, and can go from low to high. Just a little bit of signals. Right? So the most significant bit of my data set, I chose to put them in this order, so it would be my first bit of my customer data. That goes from low to high at most once over the course of the data set. There's actually some very nice encodings that we can get for data that's this heavily correlated. It's much better than the zeroth order approximation. When we said this is zeroth order information here, we're saying I'm not using any information about what the preceding bit is to predict the next one. I'm just using the total number. Okay? Here I'm able to say, well, I can tell you an awful lot right up until this moment. Tell me the position it goes high. Right? One number is enough to compress, to encode this entire series because it has so much information packed into its runs. Yes?
So is this a covered index? I mean, are you storing the data in the index? Or are you...
All of my data will be in my index in the end here. So you will actually not need an original data store. Except... we're going to find that there are some cases where you want to actually keep the data around as some sort of locality preserving prefix code, LPRC or LPFC, front coding or rear coding, just so that you can answer all the questions about a given row, because it's going to turn out to be very expensive to access an individual row. You're going to basically pay disk access per bit. Like if we've thrown the data to the winds. So accessing an individual bit of an individual row in its full entirety is actually really hard with the scheme. There really is sort of an analogy to the wavelet transform when we actually get done with this. But my goal here is to answer nice aggregate queries, and in order to answer point queries, I'm going to have to actually not do... Well, it will technically be covered, but it will be redundant. Yes?
Something maybe related. How about updates?
Updates we're going to cover completely separately. I just want to do the queries first. Because updates require me to go off on a completely different tangent and drag in 30-year-old dynamization techniques, and I don't know how I will do on time. So I really want to get to the query. I want to sketch how you do the updates, and then we'll probably run out of time. Okay, so in general, though, as we go down here, as each bit worth of information progresses, this thing's kind of at most doubling in frequency. And so we can say that our runs are going to have an average length that is very large to start, and it's going to keep going until the runs get down to the point where the average run length ceases to be long enough that it's worth encoding it, and then you kind of switch to that kind of encoding. But in the meantime, we can do very efficient codings for the top levels of this. Okay, so we can beat this bound because we know something about the ordering, and that's actually turns out to be a very nice property. In particular, I leave it as an exercise for the reader, or the viewer, or the audience, that you can actually take two of these rank select structures and build a rank select structure where you can not only find the rank and select for an individual position, but you can find the start of the run of zeros or the run of ones that you're contained in. Okay? So you need to use two rank and select structures, and there's a little bit of a trick to it. But it is possible to build a rank and select structure where you can not only answer, hey, what position am I at, or what's the position of the kth one, but given that one, where does the run of ones or zeros that it's contained in start? Okay? And this becomes really easy to answer when it's run length encoded or something like that here. It becomes harder to answer in that query, and you wind up needing two rank select structures that take the same amount of space. Information theory. So, what I want to do is I want to define total sales for 2012. Let's say that we picked some compression scheme for a year's months and dates that is based roughly on the frequency of access that we expect or on the frequency of sales that we expect. And if it's sales data, it's probably relatively recent years. We don't have sales back to 2000 BC, whatever. So we're going to pick some order-preserving code that assigns high probability, high nodes up in the tree to dates that are more likely. Okay? So if we look at this as a wavelet tree, when we walk down the tree, we can stop at any given point in time and quotient out the information. We could say, well, we got here, it's F, C, or D. So if we only wanted to summarize down to a given level in the tree, or we wanted to get down to the year, but we didn't care what the month or the date was, we could just walk down the tree and stop when we get to the right code. Sorry, I'm going to make you walk back and forth. So, our year, month, and date, we might have 2012 represented as like a 5-bit code. The top of the tree is relatively short. It's a relatively recent date. It's not too far in the past. It's probably a pretty terrible code. It'd probably be about 3 or 4 bits. But 5 bits is enough to actually demonstrate the complexities that arrive in practice. So what we want is, we want to get some code that we know out of this column. And I don't care what the customer is. I don't care what the product is. I just want to aggregate over them. So we view these as I don't care. In order to get to this bit, I have to go through these don't care bits of the other columns. So I need 5 bits I don't care about of customer, and 4 bits worth of product just to get to all the year, month, and day bits. So there's 9 bits worth of information that I don't know. But 9 bits is 512 cases. So why don't I find the start and end of the runs of my row numbers for those 512 runs of rows? Okay, and that tells me a row number in my database, in my backing store, that, customer blah, 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 and product blah, blah, blah started in year 2012 and ends. So I can tell you the row number of the start and the row number of the end of the run. And now my goal then must be to answer the total sales for a given run worth of records in O1 or log sales or something. Okay? Where I'm not paying proportion of the data set complexity size. We're paying proportion of the complexity of the indexing. So we're basically paying for sort of a polynomial in the number of indexes times the length of the code that we're looking for. And then we can play some games to try and make that faster for pathological cases. Okay, I don't know if I'll have time. So we have customer year, month, day, product. And what I did was I took my data. It's in some arbitrary order. This is the order that I have is this interleaving. The bottom of the wavelet tree has my data by customer, my data by year, month, day, my data by product. And I want to answer total sales. So I have my data set, and what's happening is by doing this, what I'm doing is I'm focusing in on, say, 512 intervals out of my data, where I care about this, I care about this, I care about this, I care about this, I care about this. And there's only at most 512 of those runs worth of records that can affect my answer because of, just that doubling theory that we talked about earlier. We only went down so far. We know the choices that we're making for these 5 bits. We only have 9 unknowns. So 2 to the 9th. And what I want to do is I want to answer rank from here to here. So this is a little bit different than the rank that we used earlier. But we can implement it with the rank we defined earlier. If I can answer rank up to a given position, I can answer rank from a position to another position by taking the rank up to here and subtracting the rank up to here. That counts this information and then subtracts it off. Okay? So we can answer rank queries for ranges. And I asked you to take it on faith that I can find the beginning and end of a run by using rank and select twice. Just because I don't have time to go through the construction. But, given that, what I want to do is now I need to be able to use rank on an interval to be able to answer a query about total sales. And now this is actually something that you can do with a classic bit index. We'll just go back to a normal bit index and we'll store a bit index for each bit of my sales. We'll store the least significant bit as one bit vector, the next most significant bit is another bit vector, the next most significant bit above that. They're not in a wavelet tree, they're just bit vectors by significance. So I have my sales going across this way. I realize I put my rows as my columns, that's fine, I guess. My 1's bits, my 4's bits, my 8's bits, my 16's bits, etc., up until I run all the sales. And then this guy is going to be a bit vector representing a homogeneous choice, something like the same kind of meaning, that says, well, my least significant bit of my sales looks like this. We can deal with doubles, but we don't need to do it right here. And what I want to do is I want to answer rank for an interval, and add 2 times the rank for the interval for the next thing, and 4 times the rank for the interval for the next thing. And I can answer these ranks in a 1 times log occurrences. So I need to do log sales time to answer my sales query. And that's just because of the bits in it. And I added up my numbers sideways. I basically went like I was doing an accounting ledger. I just tallied up one column, and I went up and tallied up the next column. Okay, so with that, we're able to answer total sales in here, and in this case, 2 to the 9th log sales time. And we never talked about the size of the data set. We talked about we care a little bit about these columns, but there's some interesting properties here. If 2 of my columns, if I had customer and customer prime, where customer prime is almost identical to customer except Bob has been renamed, or just something a little bit different. You know, where instead of year, month, day, this was year, the millennium, or something. We had something where we wanted to actually have data that's heavily correlated but stored a little bit differently. Now what's going to happen is, when you actually look at the way these bits go, remember I said I could at most double the frequency of the previous one? What's going to happen is I'm going to make almost the same choices. Okay? And so I'm going to say, well, this guy was this waveform, and then the next one was this waveform. And now, if we don't make any different choices, then the subsequent bits don't pay for this redundancy. So we get kind of co-coding for free. Co-coding is the art of sort of encoding the fact that, well, this field and that field are correlated, so let's try and build a compression scheme that actually encompasses that extra information. And so it's okay to put heavily correlated columns in your index. And you only really pay for things that are far apart in sort of permutation space. And what I mean by that is we can actually describe, there's a little bit of a mathematical diversion, we can describe sort of a divergence between 2 orders. If we have the data in this order, and then we want to get the data in this order, then we can view that this wavelet tree actually, if you don't encode it with rank and select, takes space proportional to the permutation entropy of the transformation from this order to this order. Okay? And so what that means is that if these 2 orders are very similar, then that number is very small. The wavelet tree takes very little space. Okay? And so if you look at a data set as something that is in some order, where you have customer, you have year, month, date, and product over here, and you put the data in order by customer, and you wanted to resort it, you'd have to pay to sort to get it in one of these other orders, right? Whereas what we've done is we've chosen an order that is somewhere here in the middle. Like Morton order generally basically offers each one of these a chance to give you a bit, and pick something inside this polygon in permutation space. If we view like the distance from here to here as the cost, the size of that tree. This is technically a divergence, not a distance, but it's close for intuitive purposes. And so what we're saying is that Morton order picks something in here. But because one of my data sets could choose to just pass over and over again because we're not using its full dynamic range, what happens is this could get arbitrarily close to one edge. It can get really bad. If we use a compression scheme instead and we have a decent model for the data, what we're getting is each one of these guys, when it's given its turn to give us a bit, is giving us something that's worth splitting the data on. And so what's happening is it's dragging this point closer to the centroid of the polygon. So if you're looking for that sort of intuition, that's why this order is good, is because an order that's here has shorter edges to get to any of the other edges in the polygon. The sum of these three legs is less than the sum of those two legs. We're closer to the center. Okay? So that's why we care about this particular ordering.
There's only two things I care about in terms of access performance, sequentiality and cardinality.
Mm-hmm.
Right? So is your argument that you're splitting the data set in half?
Yeah, my goal is to roughly split the data set in half on each bit in an interesting way that is relevant to more queries than not. But the goal is to pay sort of only a polynomial explosion in the complexity of the query based on the number of indices that matter.
So you're measuring it in the amount of sequential access that you have to do?
My goal here is to make it so that as I walk down the tree, the bits that I'm forced to pay for the index that I don't care about are at most sort of polynomial in the complexity of the query that I'm going through. I don't actually get to kind of sequentially scan through much in here. I do it for select in practice, but the goal here is to minimize the total number of disk accesses that I need in order to answer an aggregate query.
So that's where I'm saying there is no in between. You have sequential access performance, or you can have the cardinality of the number of things you want to access. But being somewhere in between doesn't benefit you unless you're measuring, like scanning less data.
I'm saying that objectively on disk, I'm paying logarithmically in the size of the answer to answer a query about an entire data set. And I'm saying that after we dynamize this thing, I'll pay a log factor in the size of my data set for that privilege. And so paying a log factor on a petabyte worth of data isn't going to kill me. And I can still answer efficient aggregates. And I can still dynamically update the thing with a log factor update time. Is that? And so for the most part, we're going. I don't think I'm going to have time to talk about the sort of cache oblivious nature of some of these pieces that let us divide out a block size factor in practice on different caches. But I'm probably at time, aren't I? All right, let me do a quick sketch of how you can actually dynamize this thing so it can actually handle mutation, and then I think we'll wrap. All right? And so everything I've given you so far is a completely immutable data store. The dumbest thing that we could possibly do that works for making this thing dynamic is to use multiples of them. And so what we could just do is we could view the number of records that we have. This is a terrible approach, but at least it's correct. We could use the number of records that we have as a binary counter. So you have, 37 rows. There's a 32 plus a 4 and a 1. Right? So we want one data set that has 32 rows, one data set that has 4, one data set that has 1. In practice, these numbers better be much bigger. I just wanted to get the sketch. Okay? And then what I want to do is when I want to insert a row, what I could do, and this would be terrible, but it at least gives you the idea, is I can make a new file of size 1. This has all of the wavelet trees that I have, my bit indexes, etc. And I can merge these things. So I'm going to do merges on disk. So I'm basically just going to do the merge pass of a merge sort to glue this data together on disk. And I'll make a file of size 2. Okay? At no point in time am I ever mutating a file on disk. I'm always making new files on disk that are in contiguous storage. This has some nice properties from a disk utilization standpoint. So if you want to start talking about sequential storage, this is where we start getting the story. And that is that I'm always doing all of my writes to disk sequentially on sizes that are on a doubling cube. And so no matter what your erase block size is, no matter how long it takes you to spin up a spindle, you eventually get to beat that cost. So we get to be oblivious in sort of the storage mechanism here. And we can talk about that for a more traditional database set of operations later. So now the problem with this is that if I do one insert, I can have to merge the entire database. That's terrible. But the solution to that is to use a different counter. Instead of using binary, what we can use a zeroless binary number system with a non-standard representation where you use threes, but you can have a 1 or a 0 in the leading digit. And that gives you enough delay that when you do an insert, you can pay to do the log n merge steps that you need to keep the whole thing going. And it's similar to the dynamization scheme that's used in the cache oblivious lookahead array by Bender and Fort Colton and those guys. It's also the scheme that I actually use, because I described a slightly different number system than they use, is based on a dynamization scheme that goes back to Overmars and Bentley in 1983, I think, somewhere around then. And so that's useful for taking any of these kind of structures. I use it for this. I also use it for cache oblivious maps to make a cache oblivious data structure that can replace the map storage system that we use in Haskell. And it's about 4.5, 5 times faster in practice for inserts. And it uses the existing data. You get enough data to be worth doing the work, but other than that, it's just beating on constant factors. So that at least kind of sketches how you can dynamize it. Again, basically what we're doing is we're just maintaining a small number of these things. And then if I have a rank and select structure, I can concatenate it with another rank and select structure just by storing, well, what's the rank at the end of each one of your tables, and kind of logically split and do the lookup in both. So if I make a complete binary tree out of these individual files, I can logically index into the larger structures if it was just one big rank select structure. And I pay, I have log n files, or 3 log n files, in a complete tree. So it's log n to walk down that tree to get to the thing that I care about and to answer the query. Supporting deletes requires a bit of an inversion. You actually wind up using like a separate bit vector to split out what things are deleted, and then you need a second shadow copy of the trees of what you deleted, and use ranks to do selects and selects to do ranks, and it gets complicated. But that also can be done. So you can support rank, you can support inserts, you can support deletes. The thing that kills you is schema changes. If you need to change the convention scheme because you modeled poorly in the first place. I don't have good stories for those. I'm still building the toolbox. And I'm kind of inviting other folks in to see what I have to play with. That is really what I wanted to get through today. Any other questions? All right. Neil? Yes.
Is there any story on like how close you are to?
So there is a very good story that comes out. So wavelet trees actually come out of string compression, trying to work with compressed string indexes. That's where they were originally discovered. It turns out if you take one of those, when I was using that bit vector before, wherever the heck I shoved it, this thing, or that string over there, if I take that thing and I run it through the Burroughs-Wheeler transform first, instead of getting 0th order entropy, I get kth order entropy for all k. So it's kth order empirical entropy. So I can say that I can perfectly hit 0th order entropy here. And when I start talking about it in this form, what I get is that there exists a k for which I give you kth order entropy because of this sort of walk down the tree effect. And that k gets larger as your data set gets larger. It's not as compelling as the string search story, which says, hey, for all k, we get